Today we're going to begin investigating a new quantity known as force. In physics, a push or a pull on an object is called a force. It's represented by the symbol capital F. It is a vector quantity. It has both direction and magnitude. The magnitude of a force is measured in units called newtons. Now, if there is an unbalanced force acting on an object, that will cause a change to its motion. Observe here in Figure 1. Here's a book resting on a table. We're going to apply some forces to this book. If I push on it with my hand, you'll see at the very beginning it's at rest. As I continue to push on it, the velocity will increase. It's accelerating, as we talked about in the previous unit. Now, there's different types of forces. We will observe these in this Figure 2. Here's a book resting on a table with your hand pushing on it. Now, if we look at systematically all the forces acting on that book, you can see there's different types of forces. One of them is my hand pushing on the book. Another is the table pushing upward on the book. These types of forces where two objects are in contact with each other are known as contact forces. There's another type of force. There's the mass of the earth pulling down on the book. That's the force of gravity. That's known as a field force. That's a force between two objects that are not necessarily touching each other. There will be other types of field forces we'll talk about in the second semester with electrical and magnetic forces. But for now, the main field force we'll deal with is the force of gravity. To look at all the forces acting on an object systematically, we make what is called a free body diagram. This is just as we had done before. We do motion diagrams to represent the motion of an object. This free body diagram will help you see how forces affect the motion. So this figure will show you how to draw a free body diagram. A first step, if your drawing skills are similar to mine, we begin by represent the object by a dot. Next, we show all the forces acting on the object. Draw arrows. The arrows always point away from the object, even when you have a force pushing on it. In this case, on the left side, I'm holding a heavy ball in my hand. On the right side, there's a string pulling up on the ball. In both cases, the force of gravity is pointed downward, it's the downward arrow. The upward force is represented by the up arrow. So make the length of each arrow proportional to the size of the force. So often you'll draw these before you know exactly how big the forces are, so just use your best estimate. Finally, very important step, really important coming quiz time, make sure to put labels on each of the forces. A capital F for force, the subscript will say what type of force it is. Finally, we choose a direction to be positive and indicate this on the diagram. In this case, we have the upward direction being positive. That's a common convention. If you're pushing something sideways, you might say going to the right is the positive direction. Right, so we combine forces. As you saw in this diagram, there could be multiple forces acting on an object. To see the total force, what we do is we take the vector sum of all the forces. So let's look at a couple of different situations. Here are two people pushing on a table. They're pushing with equal and opposite forces. So even though each of them are applying 100 newtons of force, because they're pushing in opposite directions, the net force is the vector sum of all the forces. As you recall, when we add vectors of equal vectors in opposite directions, the net force is going to sum to 0. If these two people apply forces in the same direction, then the net force will be the vector sum again. In this case, it would be 200 newtons going to the right. We could also have two forces of different magnitudes in opposite directions. In this case, 200 newtons to the left, 100 newtons to the right. The net force, in this case, again, is the vector sum, 100 newtons to the left. So if we apply force to an object, what is this going to do to the motion? So there's a couple ways that we could do this investigation. One of them would be to pull on an object with a spring scale. If we apply a different amount of force, how will that affect the motion of the object? If we graph the motion versus time, you can see our favorite velocity time graphs. These different situations where there's different amount of force, that will cause the velocity to change over time in a different manner. The greater the amount of force, the greater the acceleration. So we can plot the acceleration versus the force. See, in these different situations, you can see increased force causes an increase in acceleration, and in fact, they're directly proportional. Doubling the force will double the acceleration. 3 times the force gives you 3 times the acceleration. Cool. There's also something else. You saw this in the Pull This lab. There's something else that we can do to change the acceleration of an object. If we were to change the mass of the system, in this case, I could pull with a certain amount of force on a single cart, then I could stack another cart on top of it, stack 3 carts, just change the amount of the mass. What will that do to the motion? If we look in this case, the acceleration, you can see that you will have a smaller acceleration versus force when the mass increases. In fact, the slope of the acceleration versus force plot is equal to the reciprocal of the mass. We'll investigate this in more detail in the lab that we'll do next week. So this can be expressed mathematically several ways. One would be the acceleration is equal to, let me back up here, acceleration is equal to the net force divided by the mass. You can also say that force, net force, is equal to mass times acceleration. Because this is true, a Newton can be expressed as a unit of mass times acceleration, so 1 Newton is equal to 1 kilogram times meter per second squared. So this mathematical expression is known as Newton's second law. So you can observe different situations. In this case, in the figure below, you can see that we have 2 dogs pulling on a sled, each of them applying 40 newtons of force in the same direction. The net force, the vector sum, is 80 newtons. So Newton's second law, again, is the mathematical expression of the fact that the acceleration is equal to the net force, the vector sum of the forces, divided by the mass of the object. So to solve problems with Newton's second law, there are several steps. First off, we may have more than one force acting on the system, so you have to add all the force vectors together to determine the net force. Draw the free body diagram that we just talked about, get the direction and magnitude of each force acting on the system, add the force vectors to find the net force, and then use Newton's second law to calculate the acceleration. So what happens if the net force is 0? Now, as you can recall from Newton's second law, if the net force is equal to 0, acceleration is equal to 0. However, that does not necessarily mean that the object isn't moving. Recall that acceleration means the change in the velocity of an object. So if an object is sitting still, if there's no motion on it, and there's no net force, it will remain at rest. However, if an object is moving, if it has some velocity, if it's moving with some speed and direction, and there's no net force acting on it, it will continue to move with that same speed and direction. Newton expressed this systematically by saying an object at rest will remain at rest, an object that's moving will continue to move in a straight line with constant speed if and only if the net force acting on that object is 0. So figure 8 in your book is a video depiction of Newton's first law. Here we have a coffee cup sitting on top of a car. That car starts to move in a straight direction, then it goes around a turn. As it changes direction, that coffee cup wants to keep going in a straight line. So let's see what happens. Yes, that coffee cup wanted to keep going straight. So that illustrates how Newton's first law works. So that's what we have for today. So finish reading over this section, get going on the first launch homework.